The next question we must address is, how does the Fourier transform work? In order to begin tackling this, I'd like to ask you, how would you work out how many cents are in €1? Well, you would divide €1 by 1 cent and you would get 100 cents. How many eighths are there in 64? You would divide 64 by 8 and find out that there are 8 eighths in 64. How would you find out how many 6 Hertz signals are there in your particular function, let's say of time? Would you, for example, divide your function by 6 Hertz? Now, I'm suggesting that that sort of operation is what gives you the Fourier transform. You're simply dividing your signal by the frequency components, or your frequency basis vectors, frequency basis functions. And perhaps that's what's going to give us the Fourier transform. But how would we do that? How would we begin to divide a signal by a frequency? What does that even mean? Well, before I do that, I must do an important aside, and it's about Euler's formula. In this aside, we will see why in the Fourier transform integrals, it's equivalent to integrate a cosine, a single cosine, and a complex exponential e to the I theta. In order to do this, we require Euler's formula. I've derived Euler's formula in complex numbers, video 3 of 4. So if you're not familiar with Euler's formula, that video is a place to begin, or a good starting point. Euler's formula is stated here. We say that e to the I theta is equal to cosine theta plus I times the sine of theta, where I is equal to the square root of minus 1. Now, the Fourier transform integrals involve two particular things. The first one is infinite but even integrals. Of course, they go from minus infinity to positive infinity. And they also involve products and sums of cosines and sines. Now, the products and sums of cosines and sines, using some clever trigonometric identities, can be written as a single cosine. So, as we will see later when we look at the derivation of the Fourier transform, instead of having 4 terms, namely 2 cosines multiplied together, added to 2 sines multiplied together, we can rewrite this as a single cosine of a minus b, let's say, or of course we can equivalently say that's cosine of theta. Now, I said that there were two important parts of the Fourier transform integrals. The second part, or well, the first one that I mentioned, was the fact that the integrals themselves are even. Furthermore, we note that sine theta is an odd function, and inside an even integral, it will integrate to 0. So a moment ago, we saw that we are able to rewrite the products and sums of cosine and sine as a single cosine, which of course is inside our infinite integral. Now, because sine itself is an odd function and will integrate to 0, what would happen if we added anyway to the cosine I multiplied by sine theta and integrate it? Well, of course, that's going to be nothing else as integrating cosine theta. So it's equivalent to integrate cos theta plus I times sine theta and just simply cosine theta. I'm sure what you can see coming, and namely we're going to invoke Euler's formula. So as I said, e to the I theta is equal to cos theta plus I times the sine of theta. This means that inside the Fourier transform integrals, we can go from having a single cosine, or integrating our cosine, to integrating e to the I theta. So when I say theta here, by the way, I really mean cosine a minus b, which came from having cos a and cos b and sine a sine b. Of course, once again, we will see that later on when we try and derive the Fourier transform proper. The reason it's useful to go from using the trigonometric function cosine to complex exponentials is that complex exponentials are very easy to manipulate. So the point here is that e to the I theta is both a cosine and a complex sine. However, inside the Fourier transform integrals, it integrates exactly as a cosine. So now it's time to go back to our question. how many 6 Hz signals are there in our function f of t? Well, let's divide our function f of t by cosine of 6 Hz. Now we saw a minute ago that cosine when you're using these even infinite integrals is the same as doing cosine 6t plus I times sine of 6t, because the sine is going to integrate to 0. So we just swap it and put in e to the I 6t. But we can bring this part of the expression above the line provided we change the sign on the argument. So we have f of t multiplied by e to the minus I 6t. So what that means is that f of t multiplied by e to the minus I 6t is the same as dividing our function by cosine 6t in this particular case. But this is also only at a particular point in time. So let's extend it to all time by performing an infinite integral. And what do we get? We have the infinite integral of f of t multiplied by e to the minus I 6t dt. And I'm wondering, is this in fact the Fourier transform of f of 6? Or is this, this is the Fourier transform of it. And it turns out, of course, that that is exactly what we saw at the very start. So we're seeing that all the Fourier transform is doing is dividing our signal by the basis functions and the particular frequencies. I'll of course be more rigorous at a later stage.